Last week, I made a video taking a look at true sine wave inverters. And in that video, I mentioned that we used something called a phase-shifted full-bridge converter to create the high-voltage DC. But phase-shifted full-bridge converters are everywhere. Almost every high-power device uses a phase-shifted full-bridge converter. But how do they work? Let me first show you the circuit diagram for a phase-shifted full-bridge converter, and then we can take a look at how it works. The circuit diagram is pretty simple. It consists of 4 switches arranged in a full-bridge arrangement, which is where it gets its name. A full-bridge arrangement basically means that there's a switch between the positive line and the negative line for each of the output lines. And in the case of a phase-shifted full-bridge converter, the output is the 2 ends of a transformer coil. On the other side of the transformer coil, we place some kind of rectifier, either a full-bridge diode rectifier or a full-bridge or half-bridge MOSFET rectifier. Now that we know what the circuit looks like, let's take a look at how it works. This is a simple single-phase inverter. When we turn one of the MOSFETs on, it will connect the power to either positive or negative. If we turn the top MOSFET on, it connects the output to positive. If we turn the bottom MOSFET on and the top MOSFET off, it turns the output to ground. Now that we understand how that works, let's take a look at why we would ever want to do this. So, let's take a look at example A, where the top MOSFET on the first circuit is on and the bottom MOSFET on the second circuit is on. In this example, current flows from the positive wire on the input through the first MOSFET, through the transformer, and then through the second MOSFET to ground. Effectively, the voltage difference over the transformer, if we ignore losses, is exactly the same as the voltage difference between our 2 input wires. Now let's consider another state where both the top MOSFETs are on. In this case, both wires on the transformer are the same voltage and there is no voltage difference between them. This means that no current will flow. The third state we can look at is if the top MOSFET on the second circuit is on and the bottom MOSFET on the first circuit is on. In this case, pretty much the same thing that happened with the first case will happen, however, in reverse, with current flowing the opposite way through the transformer. The final state that we can observe is when both the bottom MOSFETs are on, when once again the transformer will have no current flowing through it because both sides are at the same voltage. Now let's take a look at these 4 states together. You can see that they kind of go in a cycle. Let me explain what I mean. States 1 and 2 are the exact opposite of states 3 and 4, kind of the inverse. But we're going to ignore states 2 and 4 right now, because I want to explain a simple converter using a square wave where we only use states 1 and 3. As we rapidly toggle between states 1 and states 3. However, because this can take place at a much higher frequency, up to a megahertz as opposed to the 50 hertz of mains electricity, we can use much smaller inductors. It's almost perfect, but this converter has a problem. There's no way to change the voltage. We don't have a duty cycle here. We're simply adding energy to the primary and taking it out of the secondary at the same time. Let's now consider a quick addition to this. Instead of turning directly between state 1 and state 3, positive and negative, we instead have a second stage in between where we pause, and during this stage the connection is 0 volts. You know what was 0 volts? State 2 and state 4. So now when we cycle through our things, we go plus 12 volts, 0 volts, minus 12 volts, 0 volts. And the time we spend at 12 volts is our duty cycle. Now I get to explain to you why this is called a phase-shifted controller. It's all in the controlling of the circuit. Let's take a look at one side of this inverter for a second. This is getting a little difficult for me to draw in Premiere Pro, so I'm going to model it in some electronic software. If we take a look at the first inverter, we control this with a square wave supplied to the top MOSFET with a 50% duty cycle. We then supply its inverse to the bottom MOSFET. In order to do this, we can use a NOT gate. Next, we can rebuild that circuit and add it to the second inverter. Now let me explain the control to you. In order to help you better understand this, I've slowed this simulation right down. And currently, both our inverters are perfectly in phase. So whatever this inverter does is mirrored exactly by this inverter. Now, because our signals are in phase, we've got 0 volts on the output. We effectively have the same thing happening twice. But if I change the duty cycle on this, let's say to 1 degree of offset, now every time it switches, this second MOSFET or second inverter is switching 1 degree after this first one, and that's causing these little voltage spikes. If I push it more out of phase, let's say 90 degrees, you'll see that it switches considerably after the first inverter. In this case, we're switching exactly halfway through the wave, and this generates a 50% duty cycle. On my website, I have this really cool tool that allows you to visualize the output voltage of a phase-shifted full-bridge converter. So, we have some parameters here. The input voltage I've set to 12 volts, and I've set our transformer to have a 60:1 or a 1:60 windings ratio. Now, as we increase our duty cycle, our output voltage increases. For a true sine wave inverter, with this particular setup, we'd be looking at about 55% duty cycle on the output at 12 volts. But when the batteries decrease, they might go to 7 volts, in which case we'll need a higher duty cycle. It's around 95% if I'm not mistaken. And the same goes if we overcharge our batteries and they're a bit higher. At 14 volts, we simply drop our duty cycle to around 48%. But now I'm sure the question is, why do we use phase-shifted full-bridge converters as opposed to half-bridge or full-bridge converters with hard switching? Well, the main advantage is the fact that they have zero voltage switching, or ZVS, which basically means that there's no voltage when the MOSFETs change from a high to low state, which drastically increases efficiency and decreases wear on the MOSFETs. It also requires some pretty fancy design using the leakage of the transformer. Anyway, that's it for today. If you'd like to see me actually put this to work and build a true sine wave inverter, stay subscribed because that's coming. It's going to be a while, but it is coming, I promise you that. Alright, see you guys soon.